In this lesson, we're going to be exploring some basic integration problems. But before we do that, let's do a quick review of what we know about antiderivatives so far. All right, so if I have capital F, all right, so that's the antiderivative. If I know the antiderivative is x to the fourth, and I take the derivative of the antiderivative, I get 4x to the third. Now, if I integrate 4x to the third with respect to x, I get x to the fourth plus c. So don't forget this plus c. We talked about this being a common mistake a lot of students make. So don't forget the plus c. All right. So so we learned that differentiation and integration are inverses of each other. If I integrate a derivative, I just get the antiderivative. And again here, if I take the derivative of an integral, I just get that function. So they cancel each other out. Okay, now I pulled these rules from a different textbook, the Larson Calculus book. It's a little bit more in-depth than our Hayes and Harris book, and but it includes all the rules that you need to know. The only ones that you don't need to know are these last two, the integral of cosecant and cosecant tangent. But the rest of these you should know and should already be familiar with in some way. And we'll go ahead and I'll go through these one at a time. So if I take the integral of 0 with respect to x, well, what derivative gives me 0? Well, the derivative of any constant gives me 0. So the integral of 0 is a constant. K stands for constant also. So if I have another number besides 0, so maybe 7, the integral of 7 with respect to x, well, how do I get just 7 when I find the derivative of something? Well, when I have 7 times x, right, if I have 7x and I find the derivative, that just gives me 7. So when I integrate just a number, some sort of constant, I get that constant times x plus c. Now if I have a constant times a function, it's the same thing as integrating just a function and then multiplying by the constant afterwards. Okay, and there's a proof for that in your textbook if you want to make sure that that's correct or that's true. Another rule is if I have the integral of a sum of two functions, or the difference of two functions, I can split that into two separate integrals, right? And integrate each of them one at a time. Now this is our power rule, right? If I integrate x to the n, let's remember that the power rule worked that I would do over here, I would multiply by n and then subtract 1 from the power. So knowing that, what I'm going to do is I'm going to add 1 to the power and then divide by the power, because I know if I were to integrate, if I were to differentiate this, I would have to do n plus 1 times this, and so these two have to cancel out. The times and the divide have to cancel out to give me just the x to the n. You might want to pause and take a closer look at this, because this is going to be probably the most important rule for you for this unit. And then against the derivative of sine and cosine, so the integral of cosine is sine plus c. And then the derivative of cosine is negative sine, so the integral of sine is negative cosine. And then all these are also the reverses of what you already knew. The derivative of tangent is secant squared. The derivative of secant is secant tangent. So when you see the integral of secant squared, you know it's just tangent plus c. All right. So these rules should feel instinctively natural to you. So what we're going to do now is we're going to go ahead and practice some problems. So I have this that I made. These are not example problems from your textbook, so this is in addition to what you already have in your textbook. So it says integrate. So here we go. The integral of 1 over x cubed dx. Well, that doesn't look like any of our rules that we had before. That doesn't fit any of the rules that we had. Okay. So what are we going to do? What we need to do is we need to practice transforming. Um, the main idea from this point on is that you don't have to integrate just what they give you exactly the way it is. You can do some playing around with this before you integrate. And in fact, the more playing around with the term here, the more simplification you can do, the better. So for example, you should recognize that this is the same thing as x to the negative 3 power. Now we can just use the power rule. Right, so what we'll do is we'll take this negative 3 and we'll add 1 to it, and then that'll be negative 2, and then we're going to take our answer and divide by negative 2. All right, and we can check to see that this is correct by taking the derivative of this. If when we take the derivative of this we get 1 over x cubed, then we've done it, then we have the right solution. All right, so our final answer, you can leave it like this, or to change it back into the original form where it was the exponent was a positive exponent, then you can take one more step and move from here to here. All right, so we have integrated. All right, so that's the result. Now over here, take a moment, pause, and see if you can find the integral of this. Okay, so hopefully you realize that we should adjust the integrand to be a fractional exponent like this, and then we just apply the power rule. We take this and we add 1 to it. That gives us x to the 3 over 2. Of course, we're going to have to divide by 3 over 2. Don't forget plus c. And then we can simplify that. All right, and we get something like this. Okay, so so that's the answer to that one. Now let's try C over here. I want you to hit pause and try to find the answer. Okay, so first of all, we don't have anything for 2 sine of x, but we have a rule that says we can take this 2, put it out in front of the integral sign, and just worry about integrating sine of x. And so that should be your first manipulation that you do. So these two will give us exactly the same answer. Right? We know that the integral of sine is going to be negative cosine, so our final answer looks like this. Okay, let's try some more. What if I get something weird like this? The integral of just d to the x. Well, hopefully you realize that there's an invisible 1 here. So the integral of 1 times d to the x, well, 1 is just a constant. What do I, so pause and see if you can figure the rest of this out. Okay, well, the integral of a constant is just a constant times x. So our constant is 1, so it's just going to be 1 times x plus c. All right, moving on to this example. Pause and see if you can do this one. Okay, what I think we should do here is we should break this into 2 separate integrals. The integral of x plus the integral of 2. The integral of x just becomes x squared over 2, and the integral of 2 is 2 to the x. So we just add those together and add plus c at the end. Okay, let's do a polynomial. Pause and see if you can figure this one out. Okay, so once again, just like in the previous example, what we're going to do is we're going to integrate each of these separately. So the integral of 3x to the 4th is going to be x to the 5th, 3x to the 5th divided by 5 minus, and then the integral of this is going to be x to the 3rd over 3, and then plus x squared, and then plus c. Always remember the plus c. All right, let's do something a little bit harder. Integrate this. Pause this and see if you can figure out something for this. Okay, hopefully you realize that we need to rewrite this in a way that makes more sense for us. And what we could do is split this into 2 separate fractions. All right, so we should separate it into x over x square root of x and then 1 over x. And then that should look a little bit more familiar because I can actually combine this into one expression, right? X to the 1/2. And then this in one expression, x to the negative 1/2. Now I can just split that into two separate integrals and add them together, do some simplifying, and of course don't forget c. You don't have to do this last step where you factor out the square root of x. You could just leave it just like this or convert this into some sort of radical square root sign since that's what you started off with. But this would be totally fine here. Alright, let's try this again. Alright, pause and see if we can figure this one out. Okay, so what do we do here? How can we simplify this to be something that makes a little bit more, looks a little bit more familiar to us? Well, we can take this cosine squared and separate it into two separate cosines. So then we can have sine over cosine and then 1 over cosine multiplied times each other. Well, we know 1 over cosine, see, this is very tricky. If 1 over cosine is secant and sine over cosine is tangent, we know that there's a derivative that gives us secant tangent, and hopefully you remember that's secant. So secant squared plus c. Okay, so those are some example problems of integration, some basic integration. What we'll do is maybe you can look over the example problems in your textbook and see if that makes a little bit more sense to you. And then you should have a nice foundation to go ahead and get started. We can't do example 7 type of problems yet. That'll be in our next example, next screencast. So go ahead and play around with this a little bit more and hopefully it'll be helpful.